Welcome to Math with Malia. Today we're going to do the enVision Algebra, Topic 10, Lesson 2, learning about the cube root function. The last lesson we learned our square root function, and today we're going to learn another new function and talk about key features and how translations affect the function. Amelia wrote several radical expressions on the whiteboard. So part A, evaluate each expression and explain how to plot each value on a real number line, So if we're just going through and evaluating these, we know the square root of 49 is 7. The square root of 27 is 9 times 3, and the square root of 9 is 3, so this would become this 3 times the square root of 3. The cube root of 27 is 3. The cube root of 72, so remember we can break down 72 into its factors. Of 8 and 9, and I know 8 is a perfect cube, so the cube root of 8 is 2, and then we're just going to leave the cube root of 9 in there since that's not a perfect cube. Square root of 2 will be a decimal. It's an irrational number. Square root of 16. Wait a minute. We can't take the square root of a negative number, so that can't be graphed on a real number line. Cube root of 3, it will again be a decimal, but we can graph that. And can we graph the cube root of negative 16? Well, remember, if we have cube roots, I am multiplying the base 3 times. So is there a number I can multiply 3 times to get a negative? Yes, we can take the cube root of a negative number. So we can graph all of them except the square root of negative 16. All right, key features of the cube root function. What are the key features of that parent function? Okay. So again, since we are talking about cube root function, let's choose input values that are perfect cubes. And since it's a cube root, we can have negative inputs because I can take the cube root of a negative times a negative would still give me a negative. So here's our table of inputs, -8, -1, 0, +1, and 8. And if we evaluate, take the cube root of each of those inputs, we get -2, -1, 0, 1, and 2. And we can graph those. And you can see that the graph looks like a stretched out S, if you will. Okay, it looks like the square root function on this part, but then we have this part that can go negative inputs and outputs because it's a cube root. Okay. As the value of x increases, meaning as we move to the right on our graph, the cube root function also increases, or the outputs also increases. So this function is always increasing. What about the domain and range? It doesn't seem like there's a limit. It's just going to go on and on to the right and on to the left, and it keeps increasing. So our domain would be all real numbers, and the range would be all real numbers, since we can have positive and negative output values. Okay, evaluating maximum and minimum values for a function. Since it's always increasing, we can only look at maximum and minimum values within a given interval, okay, within a section of our function. So here we're going to look at the interval from -8 to +8. So if we start at -8 and we go to +8, just that section of our graph, what would be the minimum value and what would be the maximum value? Again, as we are moving to the right, we know that our graph is always increasing, so our minimum value would be farthest to the left, and our maximum value would be farthest to the right. So essentially, if you're given an interval of the cube root function, the minimum will be the first endpoint of the interval, and the maximum would be at the second endpoint. Okay, so you can evaluate those inputs and find the minimum and maximum values for the output. Could we do the same for all functions? Well, not necessarily. All functions are not always increasing. Take the quadratic function, for example. We make a parabola, so it is decreasing and then it is increasing. So we can't determine a minimum or maximum within a given interval. And it might even be the same if we are choosing our interval symmetrically across the axis of symmetry. So this rule works for always increasing functions like the cube root function. Try it number 1. What are the maximum and minimum values of the function cube root of x over this particular interval? So again, we're going to evaluate the endpoints and find the minimum at the farthest left input, and the maximum will be the output at the farthest right endpoint. So if we evaluate f of negative 27, the cube root of negative 27 is going to be a negative number, and it will be negative 3 times the square root of 3. And if I evaluate positive 27, substituting my input into my function rule, this would be positive 3 times the square root of 3, just like we did in the beginning slide. Example 2, how does the graph g of x equals the cube root of x plus 4 compared to the parent function? So now we're going to look at translations just like we did with our previous functions and like we did in the previous video of square root functions. Let's look at the change. The change is happening outside the parentheses. The change is happening to the output. So this means it is a vertical translation. I am shifting the graph vertically. And we know, since it's positive, I'm going to move every output up 4 units. So you can see in the graph that the function g of x is shifted up 4 units from the parent function. So again, once we add a constant to the output of a function, it shifts the graph vertically. Okay? And this function rule looks similar to the other functions when we do vertical translations, plus k plus a constant on the outside of our function rule. Now we have a change to our function rule happening inside the parentheses, or the change happening to the input. So this is going to be our horizontal translation because I'm shifting the graph along the x-axis. I'm shifting it along the input values. And remember, the plus 6 means that in order to make g of x match up to the parent function f of x, I have to add 6 units to make it match up to the parent function. So in order to add 6, I have to start 6 units to the left. So this is a horizontal translation where we have moved the whole graph 6 units to the left. And just like with other functions, subtracting a constant from the input is a horizontal translation, okay? And it follows this general formula. And the reason why it's subtracting, that tells us we're moving in the opposite direction. Okay, so subtracting the constant moves us in the opposite direction. So in this case, I'm actually subtracting negative 6, which tells us we add 6. All right, for example 2, triads, we're just going to use our arrows to describe what happens to the graph after the change. So for g of x, the change is happening outside the parentheses or happening to the output. So I know it's a vertical translation. We're going to shift the graph down 2 units. For p of x, the shift is happening inside the parentheses or the change is happening to the input. So I know it's horizontal, and that means I'm subtracting a constant, and in order to make it add 1, I have to subtract a -1, so that means I'm moving to the left 1 unit. All right, our application problem. In general, when we are talking about volume of things, since we have 3 dimensions, we're going to be dealing with cubes and cube roots. Creative Clays is increasing the package size for its art clay. Designers are considering different sizes. Assume that the new package will be a cube with volume of X inches cubed. Okay, so our new volume is X. For what increases in volume would the side length increase between 1 and 2 inches? Okay, so we have to be careful how we're thinking because this is set up a little bit differently as far as our X and Y axes. Okay. So since the new volume is X and the old package, according to the diagram, originally was 8 cubic inches, how do we find the difference or the change in volume? I start at 8, I go to X. To find the change or the increase, I would have to subtract X minus 8. Okay, that's telling me the change. If I started at 8 and I go up to X, in order to find out how much I increased, I have to subtract the 2. So that is the increase in volume. Remember, we're talking about volume. Okay. And if we remember our formula for volume of a cube is just side length cubed, okay, if X is the side length. So then how do I find the side length? Well, we would have to do our opposite operations and take the cube root of both sides. So if I take the cube root of V, I will get the side length. Okay, so this is a part that they don't tell us, but we need to understand the relationship between side length and volume. Because since we're given the volume and we're looking for side length, we need to use this formula. We need to use our formula of taking the cube root of the volume to get side length. Okay, so we know that the change in volume is X minus 8. And if our function is going to represent the change in side length, notice our y-axis, our output is measuring the change in side length, whereas our x-axis is measuring the change in volume. Okay? So in order to evaluate the change in side length, I would need to do the cube root of the volume. Okay? So we're going to take, or the cube root of the change in volume. So I would be taking the cube root of X minus 8 to calculate a side length. Okay, according to the graph, we can see there are 2 volumes given at 9 and 16, and then 2 side lengths given if we apply that formula. So evaluating 9 minus 8, and the cube root of that is 1. And then evaluating 16 minus 8, and the cube root of 8 is 2. Okay, so they chose easy numbers on the graph. So the output again is measuring side length. So for our side length to go from 1 to 2, as it asked in the question, our volume needed to go from 9 to 16. Okay, so this one was just a little tricky in making sure we were watching how the axes were labeled. Okay, usually we would think side length would be on the x-axis, but in this case, we were making the x-axis represent the change in volume. So again, we use algebra so much in the real world, especially if we're talking about area, and we would use quadratic functions, or if we're talking about volume, we would use cube root functions. All right, try it. A cube has a volume of 10 centimeters cubed, so this is the original volume. A larger cube has a volume of x, so similar to our previous example, except now our starting volume is 10. Consider the function this cube root of x minus 10. Now remember, we subtracted to find the change in volume. So what does f of 14 represent, and what does f of 19 represent? Well, 14 represents x, and what was that representing? The volume. Okay, so f of 14 is representing the change in side length when we go from a volume of 10 to 14. And f of 19 would likewise represent the change in side length when the volume goes from 10 to 19. Example 4, rates of change of a function. We've done rates of change already with other functions, so we're going to use the same process, evaluating the endpoints for the interval and then using our slope formula to find the change in output over change of input to find the average rate of change. Again, since this is a curved function, we can't get an exact rate of change or slope at each point, so we're just going to look for the average between 2 points. Okay, our function is the cube root of x minus 1. Just thinking about it in my brain, I imagine this graph is shifted 1 unit to the right from the parent function. And we have 2 intervals. We have our interval from 1 to 5, and we have our interval from 5 to 9. So again, we're going to just evaluate the endpoints, so f of 1 and f of 5, plug in the input to the function rule, and we get our 2 different outputs for that interval. And we could do the same for the second interval, evaluate f of 5, which we already have done, and evaluate f of 9, plug in that input into the function rule, and we get our last output. And then remember, rate of change is the change in output over the change of input. I like to write it different ways. Okay, so the change in our output over the change of x. That means we're going to take our second point, our second output, and subtract the first output, divide it by the second input minus the first input. And if we substitute our numbers, there we get an approximate average rate of change for the first interval. We're going to do the same thing for the second to find the change in output over the change in input, essentially calculating the slope between these 2 points. We're going to evaluate the second output and subtract the first output, divide that by the second input minus the first input, and we get an approximate average rate of change. If we compare those 2 numbers, we can see that the average rate of change is decreasing. Does that make sense for our graph? I'm going to flip back to the parent function. This will be good. Is it slowing down? So if I were to draw a slope at this point, we can see how steep that line would be. And then if I were to draw a slope at this point, it is not as steep. So we can see that the graph is getting steeper and steeper, or the slope is getting less and less. In other words, it is increasing at a decreasing rate. Okay, so we are decreasing as we move farther to the right on our graph. It's becoming less steep as our x values increase. Okay, example 4, try it. I'm just going to help you set up the problem, and then you can practice on your own. I'll give you the answers so you can check. So compare the average rates of change for f of x when the function is 2 times the cube root of x minus 3. So just really quick, let's just think about what's happened to our graph compared to the parent function. We have shifted the graph 3 units to the right, and since we have this 2 multiplied by the whole function, we are vertically stretching the function as well. Okay, remember to first calculate the rates of change, we need to evaluate the endpoints for each interval. So we're going to evaluate f of negative 12 and f of negative 8. We would also need to evaluate f of negative 4 and f of 0. So we have 4 inputs to evaluate, and you would plug those in to the function rule. So for example, 2 times the cube root of 3. Don't forget this is negative 12 minus 3. So this would be 2 times the cube root of negative 15, okay? And you would do the same for the other inputs. After you did that, then you're going to calculate the average rates of change. And remember, rate of change is change in output over change in input. The triangle means change. So for the first one, our first point is negative 12 and our second point is negative 8. So we would take f of negative 8, whatever that value was, and subtract f of negative 12. And then we would do the change in input, which would be negative 8 minus negative 12. Be careful with our negative numbers. Okay? So that means you would be adding 12 instead. Okay? And you would do that same process for the others. Now, knowing what our cube root function looks like and knowing that we have just shifted it to the left and stretched it a little bit, what will the rates of change do as we move to the right? As we move along the x-axis, increasing our inputs, we know that the graph gets less and less steep. Okay, so the average rates of change would be decreasing. And we could do all the calculations and show that, yes, the values as we go from negative 12 to negative 8, then from negative 4 to 0, those values would be decreasing. Example 5, comparing rates of change of 2 different functions. The graph and the table represent translations of the cube root function, of the parent function. So let's look at the graph representing function g. We can see that it looks like it has moved to the left, okay? And looking at the table, we don't have a graph, but we know it is a translation as well. We don't have a scale factor, we don't have a vertical stretch or a horizontal stretch. Which function has a greater average rate of change over this particular interval from 2 to 4? So we can look at the graph going from 2 to 4, but we can't really get accurate output values, so we do need to evaluate those. Okay, so we have to evaluate g of 4 and g of 2. Okay, again, our second point minus our first point. And if we substitute those numbers into the function rule, take the cube root of 4 minus the cube root of 2 and divide it by our change in input, here is our average rate of change for g of x, the function represented in the graph. For the table, they've already given us the output, so we don't have to substitute any inputs. We just have to find where x is 2 and where x is 4. There's our interval, okay? So going from 2 to 4, how does our output change? Well, we can take 2.81 and subtract 2.48. And then how does our input change? Again, that's just 4 minus 2. And after we do the calculations, our average rate of change is 0.165. So which function, g or h, has a higher average rate of change? Well, we can see that the function h of x has a greater average rate of change in that particular interval. All right, try it number 5. Which function has the greater average rate of change over the interval from negative 5 to 0? It says the first function is a translation to the right 1 unit and up 2 units. They don't actually give us the function rule, so we need to rewrite that function and compare it to r of x. So let's call the new function g of x. What would the equation be, or the function rule be, for g of x if it is right 1 unit and up 2 units? Okay, so going right is horizontal. So I know that I have to have a change inside my parentheses, or a change to the input, and since it's to the right, that means I have to subtract 1 in order to get it back to the parent function. Okay, so it's shifted to the right, so then when I subtract 1, it will match up to the parent function. And up 2 units, that's a vertical translation. I know that is adding a constant k to the output of my function. So there is g of x, or the first function. And then we're comparing it to this function, which is just 3 units up from the parent function. So if we think about that, I'm up 3 units and then shifted to the right and up 2 units. And I'm looking at the interval from -5 to 0. Can we figure out which function will have a higher rate of change just by evaluating what the graphs will look like? What do you think? Okay, so hopefully you've spent some time looking at this. You can plug in the endpoints for each interval and do all the calculations to calculate the rate of change. I want to see if we can get there by just envisioning the graph. Okay, you could also try plotting this on your graphing calculator and see what the change is as far as what the graph looks like. So for g of x, I have shifted it to the right 1 unit and up 2. So I'm going to just try to do a rough sketch of this. So maybe it's, oh, that didn't go up 2, did it? So over 1 and up 2. There's my rough approximation of what that would look like for g of x. Let's try r of x. It's only shifted up 3, so I know it's still going to have its change point, its change in direction at 0. It's just going to be up 3 units. Better go up 1 more. Okay, oh, that turned into that. I didn't want that. Okay, there's my rough sketch. It's not too great. So if I'm looking at from -5 to 0, I'm looking at this section somewhere over here, okay? Up to 0 for g of x, it is still starting to get steeper and steeper. As you can see, before this spot in our cube root function, that's where it changes. It's going from increasing, steeper, 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 and then it starts to decrease as it moves to the right. Okay? So if I'm looking at something up to 0 for g of x, I can see that it's going to be increasing. If I'm looking at my function r of x, it is also going to only be increasing, but it gets really steep at 0. Okay, so it starts to hit the really, really steep part. So which one do you think would have a greater average rate of change? Well, probably the function that gets steeper and steeper and steeper in that interval. So sometimes it's really helpful to imagine what happens with the graph and see if that can help you answer the question to double check your calculations. What's actually going to make sense as far as the graph? That brings us to our concept summary for the cube root function. Remember, the translation rules apply the same way that they have for all the other functions that we have done. And make sure when you're doing your average rate of change calculations that you are careful with your negative values when you are finding the change in output over the change in input. I hope this has been helpful. Let me know if you have any questions or comments or what else you would like to see. And come back for some more math help and lesson overviews with Math with Malia.